Hello again. So, this is the second part of the so-called optional lecture on applications of exponential functions. So I'll talk a little bit about just a small amount of financial math, and there will be one side benefit of this. There's been some reference to this Eulers number E without a really good reason where it came from. I alluded to it somehow natural, but we'll see that naturality by the end of today. But it'll sneak up on us a little bit. So let's see it. So let's talk about interest rates. So first thing is easy enough. Let's suppose you put $5 in a bank account which has an interest rate of 10%, which you compound once per year. That means at the end of that year, you should have $5 plus another 10% of $5. So you should have this much money. $5 plus 10% of $5. So that's another way of saying 5 times 1.1. And there will be lots of computations today that I will not do by hand, but this I actually can do. 5 times 1.1, that's $5.5, and because you usually go out to the cents place, it's $5.50. In another year, you'll multiply by 1.1 again. That is, after 2 years, you'll have your $5. You'll multiply it by 1.1 after the first year. You'll multiply it by 1.1 again after the second year. And this is an instance of a computation, which I could do by hand. But because I certainly won't do the next one by hand, I'll go ahead and pull up an online computational aid. Okay, I'm back. So there it is. 5 times 1.1 to the power 2 is 6.05. So after, if you put it in for 2 years, you have increased your amount of money by more than double what you had in the first year. And that makes some sense. You reinvested more than you invested the first year. So you have $6.05. After 2 years, you have $6.05. Nice. So, if you have $5 and you put it in this bank account, which has an annual interest rate of 10% for 10 years, well, after the first year, you'll multiply 5 by 1.1. After the second year, you'll multiply 5 by 1.1 again. After the third year, you'll multiply 5 by 1.1 again, and you'll keep on doing that for each year the money is in the bank. That is a total of 10 times. But I know what that means. That is just 5 times 1.1 to the power 10. And again, I'll resort to this online computational aid to allow me to do that. I'll do that and be back in a second. After leaving this in the bank for 10 years, it looks like you more than double your money. You have $12.96.9. So let's just round that to $12.97. So in 10 years, you double that initial investment. So let's play this game in a slightly different context. So that's what happens if you have your money in an account which compounds once at the end of the year, and it compounds 10% each time. That's not the only type of interest-bearing account there is. Let's suppose you do the same thing. Let's suppose you put in the same $5 into an account that has an annual interest rate of 10%. So it's got an annual interest rate of 10%, but it compounds quarterly, so 4 times per year or once every 3 months. What does that mean? That means every quarter it will act as if you have an annual interest rate of 10%. So every quarter you should have an annual interest, you should have your interest should be 10% divided by 4. also known as 2.5%. So that means every quarter you'll multiply the amount of money in the account by 1 plus 2.5%, also known as 1 plus 0.025 or 1.025. That means that after 1 year, you multiply by 1.025 4 times, and that certainly is not something that I can do in my head, but I can do. And certainly, like all of these computer-aided computations, I encourage you to do on your own. Maybe even pause the video as I'm pausing the recording. I'll pause my recording right now. There we have it. 5 times 1.025 raised to the 4th, there it is somewhere around $5.52. Dollar sign, and let's indicate that it's approximate, 5.52. So, during the course of that 1 year, apparently, even though it's an annual interest rate of 10%, the fact that you compound it more frequently results in a better return of investment. After that 1 year, you make a little bit more. That's generally true. If you see the same interest rate, but it's compounded more frequently, that's a better effective annual interest rate. In 2 years, so that's 8 quarters, you'll multiply by 1.025 8 times. And, well, what is that? $6.09. So again, a little bit better than you did with an interest rate that is compounding just annually. Approximately. Oh, include the dollar sign. How much after 10 years? Well, after 10 years, 40 quarters will have passed. So you'll multiply by 1.025 40 times. This will result in 5 times 1.025 raised to the 40. There it is. Oh, money sign, approximately 13.40. My memory is very bad. It rounded up to 43, right? Yeah. Again, that's slightly better than you did with compounding annually. So, the idea is, if you have the general formula, if you have some initial investment, P, the principal that you put into account, with an annual interest rate R, which is compounded n times per year, then the amount, A for amount, which will be in the account after t years will be given by the formula A of t is equal to the principal. That was not an appropriate, that was a random stray mark, sorry. Principal multiplied by 1 plus the rate, which will be some number probably smaller than 1. In the above, it was 10% interest rate, so R was 0.1 in the previous example. The initial principal was 5. The rate was 0.1. And n in the example just above was 4, compounded 4 times per year. The idea is you act as though every 1 over n years, that is every time you compound n times per year, so every 1 over n years you compound the interest, you apply the interest rate, or this interest rate. But you need to convert it to how big the period is. That's 1 over n years. That's why I use the interest rate of R over N. So let's play this game. Let's suppose that you put an initial principal of $150. So there's the principal into an account which has an interest rate of 10%, which 10% is 1/10. Right, because what does percent mean? Percent means per 100. So this is a tangent. 10% literally means 10 per 100, which is, of course, 0.1, which will be compounded monthly. That is n times per year, so n is equal to 12. Then how much money will you have in this account after 10 years? Well, all we have to do is apply this formula. So we'll take the initial principal of 150, maybe I'll indicate the dollars here, times 1 plus the annual interest rate is 0.1, compounded 12 times, so 0.1 divided by 12. And in 10 years, how many times does 1 month go by? 10 years is 120 months. Also, what'll go up here is 120, but that's because that's 12 times 10. And again, that's not a computation that I would want to do manually. Let's do that. Let's ask a machine. You should pause the video now and ask your own machine. I'll type it in myself. All right, that took a distressingly long time for me to type that in, but let's just check that I have typed it in correctly. I was interested in, move this to the side a little bit so we can see, $150 times 1 plus 0.1 over 12 raised to the power 12 times 10. So that's 150 times, in parentheses, because this is all I want to be in the base of the exponent, 1 plus 0.1 divided by 12 raised to the power 12 times 10. And notice these parentheses are important. I need 12 times 10 to be in the exponent. If I don't have those parentheses there, the order of operations will say, well, you need to exponentiate first and then multiply, which will not be what I want. And that $150 in 10 years at this 10% interest rate will become $406 and 6 cents. So it looks like A of the amount of time that is passing is 10 years, is approximately $406, money sign, and 6 cents. So I want to see what happens now. So in general, as we saw above, as your the period of time, as you compound more times annually, as n gets big, we saw in the first example that the amount you make, the A of t, gets bigger even if you wait the same amount of time at the same annual interest rate. Let's see that happening quite literally right here. Ooh, that does not belong here. And by does not belong here, I mean, of course, this is supposed to correspond to n equals 365. So let's go ahead and fix that. So this quantity, nope, that doesn't work. Okay. $406.06. This quantity is about 406.06, money sign. Cool. So we want to see what happens when n grows. So let's see what happens if you have that same interest rate. You compound daily, though. So suddenly n is equal to 365 times per year. I know that really a year is maybe sometimes not exactly 365 days. Sometimes it's 366 days in a leap year. But let's just pretend that we don't notice that issue. So let's compound 365 times per year. What do we wind up with? Well, we have the same formula. P is still 150 times 1 plus the annual interest rate is 0.1 divided by n is 365. Maybe just for emphasis. N is 365, so this is n. Raised to the n times t. So 365 times 10. And if the pattern that we've noticed so far holds, that should do a little bit better than before. So the previous example was $406.06. I think I'm even going to record more digits than that, just so that I can notice something that happens. So that was 406.56224. There, that should be enough to notice what I need. Let's do the computation where we've replaced n by 365. Okay, so entered in 150 times 1 plus 0.1 over 365, 1 plus 0.1 over 365, raised to 365 times 10, 365 times 10. There it is in a pretty print format, so it's easier to see that that is what I want. And we round up with a total, which is indeed better than we had before. 407 point, and I want to go 1, 2, 3, 4, 5, 6 digits. 686 433. And the next digit is 1, so it should round down. Okay, so that agrees with the pattern we noticed. We do a little bit better when we increase the number of times we compound annually. So if we do that much better when we go from 12 to 365, so that's like a 5-fold increase in the number of times we compound, what if we go from 365 to 10,000 times per year, to 100,000 times per year? And maybe we'll even go on to n equals 1 million times per year. Otherwise, the exact same setup. So I'll pause for a moment. I'll write down the resulting formulas. You should also. Then I'll pause again and do the computations, and we'll see what we notice. See you in a second. Okay, here we go. We're back. So when we compound 10,000 times per year, the principle is the same. P is still 150 times 1 plus the interest rate R is still the same. 0.1 divided by n, 10,000, times the number of years that have passed, t, times n, 10,000. Similarly, when we compound 100,000 times per year, the only thing that changes is that 10,000 is now 100,000 in both of the places that it appears. If we compound 1,000,000 times, there we see it. And of course, you won't ever find an account that compounds 1,000,000 times per year, because they'll just go on to what happens on the next page because of something that we are about to notice. So let's see what these numbers actually are. Right, if you want to know what the best way, you care about how much money you have at the end. You don't care about this formula that tells you how much money. You care about what the actual bigness of that number is. And let's go ahead and check that out. I'll pause it and be back in a second. Right, here we are. So I've pulled up all four of the computations that we've mentioned. What we get when we compound 365 times per year, what happens when we compound 10,000 times per year, 100,000 times per year, 1,000,000 times per year. And here are the actual numbers. 407,686. And that agrees with what we wrote down previously. I apologize. That is an alert telling me that it is about time for me to have class. When we compound 10,000 times per year, it looks like we get $407.74 at the end. So that's less big a jump than we saw previously. So going from 365 to 10,000, oh, maybe it's about the same size. It gave us a jump of about $1. Going from 10,000 to 100,000 gave us an increase of, well, nothing that we would notice if we round to the nearest cent. And going from 100,000 to 1,000,000 times gives us a difference that we can't even detect if we go out to the tenths of a penny place. So writing those down. You don't need to watch me write them down. Okay, we're back. So we notice something. Even when we made the jump from 100,000 times compounded 100,000 times per year to 1,000,000 times per year, we don't actually see any noticeable change in payoff. So as you compound more and more times per year, sure, your total return of investment goes up, but it goes up by a smaller and smaller amount. As a consequence, there's some limit that happens. When n gets really, really big, you cease to notice that n is getting bigger at any fixed scale. It looks like it's getting close to a single number. And here is where Euler's number shows up. If you put a principal P in a continuously compounding interest-bearing account with an interest rate of R, annual interest rate R, for T years, then the amount that you have after time T is just given by the principal P times E, Euler's number, raised to the R times T. And that may seem a little bit strange, but let's go ahead and notice that this does, in fact, something quite correct. So let's look back at the previous example. I know this isn't literally in the notes. You'll have to do this, off to the side, maybe in your own paper. So let's see what happens when we have an initial principal of $150. I know the dollar sign is supposed to go before, but there was no space. N isn't, we're compounding continuously, so in some sense n is infinity, but you wouldn't actually write that because that doesn't tell you anything. The interest rate is 10% per year, also known as 0.1. Then let's see what happens after a total time of 10 years. So this rate is maybe 0.1% per year, 0.1 per year, so 10% per year. T is 10 years. So that means that A should be equal to P, 150, times E raised to the R, 0.1, times T, 10. Let's see what that is approximately. Again, I'll pause and write down the computation. Okay, we're back. So, there it is. There's a computation of 150 times e to the 0.1 times 10. Maybe you notice that 0.1 times 10 is 1, but that's not the important thing to notice in this example. What do we get? We get something that is approximately 407.742. Hopefully that number seems familiar. Oh, that's interesting. That is the same up to the thousandth place as the computation we got when n equals a million, or when n equals 100,000. Interestingly, I think it's because the text went over this web page frame. It apparently obliterated what I wrote, but you saw what I wrote and you wrote it down on your own. So that's, notice that that's something interesting. There's no reason to have an interest rate that compounds 100,000 times per year. All you're doing is asking for computational difficulty. Instead, you can use a continuously compounding interest rate, which does a good enough job approximating it. There you are. So there's one last thing that I want, in fact, you guys to do. So let's suppose you put $100 into an account with a 5% interest rate. This is the first time we've seen an interest rate other than 10%. Obviously, interest rates other than 10% exist. In fact, 10% is an unreasonably high interest rate for like a savings account. You're not going to find that in the real world. That's more like what you would like hope to get in terms of a stock market investment, though right now that seems to not be the case. Anyway, my own woes aside, so let's suppose you put $100 into an account with an annual interest rate of R, which is compounded either annually, so that's once per year, 5 times per year, 24 times per year, so I guess that's twice per month, 365 times per year, 100,000 times per year, or continuously compounding. Let's see what these numbers are, how they compare. So, I encourage you to stop the video right now, do this computation on your own, because in fact you're more likely to do it correctly than I am. So I'm going to pause. I'll do my computation while you do yours. Pause. So you may have noticed some rumbling right there. There is a cat who is becoming very involved in today's lecture. She is a highly disruptive student, and I don't think she's paying much attention to the lecture itself. There she goes. She is also actively attacking the writing feed that I've been using. This is my recording setup. I've converted a guest room by putting a bed on its side and putting up a table. It's also impossible for me to get a haircut at this stage. You don't need to know all that. Okay, and now back to the actual content of the lecture. So, what have I written right here? Let me go ahead and get rid of that. So I've put down the formula for growth in an account due to interest. A is equal to principal times 1 plus the interest rate divided by the number of times you compound per year, times the number of times you compound per year, times the number of years. In this instance, the principal is $100. I've suppressed the unit. The interest rate is 5%. The time elapsed is 5 years. So if we compound once annually, we get 100 times 1 plus 0.05, the rate, divided by 1, n, times 5, raised to the power 5 times 1. And in these successive times, the highlighted 1 is just being replaced by 5 when n is equal to 5, by 24 when n is equal to 24, by 365 when n is equal to 365, by 100,000 when n is equal to 100,000. And then we continuously compound in the last instant. So in that case, there is no n anymore, because n is infinite. When we compound continuously, we have the principal times e to the RT, that's 100 times e to the 0.5, because the interest rate is 0.5, times 5. And now I'm going to pause again and do the actual computation. I won't do it in frame because that's much too slow. I'll use the fact that I have a laptop also. Okay, we're back. So, having asked a machine to do the computations, which I assume you guys have done as well, when we compound once per year, we totaled for a total of 5 years. We wound up with $127.62.8. 5 times per year, $128.24.3 cents. 24 times per year, $128, 36.9 cents. 365 times per year, so compounding every day, $128.40, almost on the nose. 100,000 times per year, $128.40.3 cents. And if we compound continuously, we actually don't notice the difference up to the tenths of a cent place. It is just ever so slightly better. So this is where the number E comes from. This is why Euler invented his number. If you model how interest rates grow when you put money into a bank, and the bank promises you that they will compound their interest rate more and more frequently, the end result stabilizes. It gets close to a single thing, and that single thing comes from this formula, and that's one way of getting at Euler's number. And that's also why it's so interesting a mathematical constant. It comes up in lots of examples like this. Wonderful. Well, I'll post this. I will see you in the future. Bye-bye.